This is a carom board. It's used to play a game called carom, a game that's very popular in India. Say we take this, called a striker, and use it to hit a carom coin on the board.
Okay, cool, but what does this have to do with rockets?
Well, let's try this again, but this time measure the initial velocities of the striker and the coin and the velocities after they collide.
It doesn't look like much, but let's try multiplying the velocities by their respective masses.
And summing up the initial values and final values. And they're almost the same.
This is a conservation of momentum, which says that the momentums of two objects before a collision are going to equal the momentums of the objects after a collision, given that there's no external force added to the system. The conservation of momentum can be extended to more than two objects.
But what if force was applied, like me pushing off the skateboard, or friction between the wheels and the ground, or even air resistance? Or even the thrust of a rocket's engine? Well, Newton's second law tells us that force equals mass times acceleration. Doing a little manipulation, we get force equals mass times velocity over delta t, where delta t is just how long the force was applied. Rearranging, this gives us F times delta t equals mass times the change in velocity, which is also the change in momentum of the object due to the force being applied. Taking this change in momentum, technically known as impulse, and adding it to the conservation of momentum and a little bit of calculus, we get the rocket equation.
The ideal rocket equation relates the change in velocity of the rocket to the change in mass of the rocket after it has burned its fuel. Since 90% of the rocket's mass comes from its fuel, the initial mass of the rocket and the final mass of the rocket after it has burned all its fuel is going to be very different.
Now let's understand what all the symbols in the rocket equation actually mean. Delta V stands for the change in velocity of a rocket. V sub E stands for the exhaust velocity of the rocket. This is the velocity at which the rocket engine ejects out the rocket fuel. Although this is constant, it's different for each type of rocket engine. The final term is the natural log of the ratio of the initial mass of the rocket and the final mass of the rocket. Not only does it tell us that if you want a greater change in velocity, you need a greater exhaust velocity, it also tells us that for a big increase in the amount of fuel used, you'll only get a small increase in the change in velocity. This is because we have a natural log function, and the natural log function increases very slowly as time goes by. This equation has been very influential to the field of rocketry since it has allowed scientists to calculate the amount of fuel needed to get to the heavens. With such a simple equation at the heart of rockets, maybe rockets aren't rocket science after all.